For a minute, we'll start. Get started. Welcome to CSE 478. I guess this is the first class of your quarter, I hope. But my name's Abhishek, and I'm the instructor for this class along with Sid Srinivasa. And our TAs are Antong, Rishabh, and we'll introduce them in a second. Right? But this is autonomous robotics, right? So the question is, what are we going to do in CSE 478? Like you've seen some description on the website, but really what we really want to do is we want to program race cars. We want to teach you how to program autonomous robots, right? And so specifically, we're going to be operating on this platform called the Musher platform, the multi-agent system for non-holonomic racing, right? And so it's basically a souped up race car, right? So we have 3 generations of this, but this is generation 1, generation 2, generation 3, and it's generally super cheap, quite fast, and pretty loaded with sensors and actuators and compute, and you can do a lot of cool stuff with it. And then so we're gonna try and get you guys to have this thing autonomously navigate around the building and teach you all the techniques you need to do that. All right, so this is the Musher car. This is you can see the evolution. We just spent more and more money after each generation, but it's pretty cool, right? So if you look underneath the hood, there's like a GPU on here, there's a camera on here, there's a lidar on here, there's a couple of servo motors, and in general, it has everything that you'd expect. It's like a miniature-sized autonomous car, right? And so the hope is to teach you the stack of autonomous cars, and from that, you can extrapolate other types of robots. And so last night, I went down a rabbit hole of what is mushing, right? So we call this thing musher. And so it turns out mushing is the sport of dog sledding. And so it's like a sport from Quebec where they basically attach a sled to a bunch of dogs and sled around. And it came from the French. But yeah, rabbit hole if you guys care. But it's appropriate given where the Huskies and our cars are trying to go fast and drift and skid and do all the cool stuff we want them to do. All right. So if you look inside the race car, right, you have a chassis from Red Cat Racing. And inside that chassis, you have like a brushless DC motor down there, a motor driver, a servo, which helps you do the steering, right? As well as a LiDAR on top and a camera. And inside for compute, you have a full-on GPU, the NVIDIA Jetson. And so you should be able to do a lot of compute. And if you want to run your neural networks on there, you can, right? And so it's a pretty neat piece of hardware. And one of the TAs from former years took this out on a dirt racing track in Wallingford and had it like do a bunch of tricks and stunts. And I'll send you guys the video. Okay. So if you complete this class successfully, the result should look something like this, right? So this is an example of the car racing around the building in maybe 2-3 years ago. I'm in Allen. And so you can see that you're down on the bottom left is the planning. And so you're trying to figure out where you are. You're trying to plan your next set of steps. You're trying to plan locally, right, in the short term, and you're trying to plan globally. You're trying to plan your course over many, many steps. And then you should be able to go really, really fast around the building. That's the end goal. Okay. And here's an example of some demos from maybe 2018 or 2019. Hopefully you can go faster than that, but you can see that like your final project should look something like that, where you're able to navigate autonomously in a new map and with no human intervention, right? So this should be fully autonomous. Okay. Also, please interrupt me with questions. Yeah, I don't like to monologue, so I'm gonna bother you with questions as we go along. But the learning objectives for this class are we're going to learn the algorithms for autonomous driving and implement them on the physical race car in 10 weeks. And so this is very much not a theory class. It's not a let's come up with a cute little algorithm and leave it class. It's a let's put things on the hardware and interact with physical robots class, right? And so we really want you to understand what the pain points are of dealing with hardware. We want you to get in and messy with the hardware and kind of understand what robotics really looks like in industry. We also want to teach you some fundamental tools, right? So robotics is not an ad hoc science. There's lots of really cool math and algorithms and things that go behind it, right? And so specifically, we're going to teach you, we're not going to teach you all the tools in robotics, but we're going to teach you a set of really important ones, right? So specifically, we're going to cover the Bayes filter, right? So things like Kalman filtering, extended Kalman filtering. We're going to cover, sorry, we're going to cover MPC, model predictive control, which is a planning technique that's used in autonomous cars. It's used in humanoid robots, in manipulators, and lots of different things. And we're going to teach you things like planning and roadmap search, which is what most industrial arms use in order to move quickly from place to place. We're also going to teach you a bunch of machine learning tools. And so, but the hope is that we're going to kind of teach you the fundamental tools that you will compose to develop your own new algorithms on these things, right? And so the hope is that the same set of tools can be used to control your drones and your helicopters and your cars and your humanoid robots. And what's kind of cool about robotics as a field is like it's kind of the same algorithms with minor tweaks that are used across everything. It's not that many bespoke algorithms. And so what are we actually going to cover, right? So the robotics is a huge space. We are going to focus on mobile robots in this class, right? We're going to focus on these race cars. We're not going to focus so much on robot manipulators, humanoids, or soft robots. I think those are all amazing. And a lot of my lab's research is on manipulators and humanoids. But in this class specifically, we're going to focus on mobile robots. So if you care about manipulators or humanoids or soft robots, come talk to me after and we'll chat about it. Okay. And in terms of techniques, yeah, go ahead.
Quickly get like I guess like definition for like what
Mobile robot is just a robot that moves. Moves as that's a bit facetious, but I think like typically a mobile robot is one that is navigating or locomoting, right? So like a car, like a legged robot that's walking around, whereas manipulators are really about like interacting with the environment, interacting with objects, right? And so maybe one way to define them is mobile robots are things that propel themselves, and robot manipulators and humanoids are typically things that propel the environment, right? And so the same set of techniques should apply with some caveats, but mobile robots are a little easier to approach to start.
What are like robotic?
There will be robot manipulators. So there are things that, like the whole point of a robot arm is to interact with the world, whereas the whole point of a mobile robot is to get from place A to place B, right? And so we're going to focus on getting from place A to place B, but in some ways you can also think of manipulating the world as taking the world from place A to place B. And so a lot of the same techniques will apply. Great questions. Cool. Okay, so given the context of mobile robots, what are we actually going to study, right? It's a big field. It's like been around for 100 years plus. And so we're not going to cover everything, right? But we're going to cover some really important stuff. So we're going to cover localization, which is the process of the robot figuring out where it is in the world, right? No one tells the robot exactly where it is. Its sensors are noisy. It has to figure out where exactly it is. So that's the process of localization. We're then going to do planning, right? Which is saying that I want to get from place A to place B. I want to navigate from here to LA. What are the steps for me to get there? Right? We're going to do control, which is saying, okay, let me convert those plans in the context of where I've localized into like the low-level system, right? That actually applies currents to the robot. And finally, we're going to cover a little bit of machine learning, right? So we're going to cover some techniques in reinforcement and imitation learning, which is a different way of kind of subsuming localization, planning, and control, right? And so that's a little more 2025. But what we're not going to cover as much of is mapping, right? We're not going to do that much mapping. There's like a whole field called SLAM, simultaneous localization and mapping, which is saying, how do I jointly figure out where I am and the map of the world together, right? Because you're an unknown, you're a robot navigating a disaster area. You want to figure out what the area looks like. You have no map beforehand. You want to build the map as you go, but the tricky part is you don't know where you are and you don't know the map. So you have to kind of figure that out together. I'll touch on it maybe a little bit, but we won't have enough time to do it in detail. We won't do a lot of computer vision in this class, so we won't cover like deep convolutional networks and vision transformers and these kinds of things. I'd recommend Ranjay's class. It's fantastic. But we're going to kind of stick to things like LiDAR and avoid dealing with camera images. We're not going to deal with low-level design of hardware, right? We're going to have this car. Hopefully you can open it up and get into the guts of it and understand how it works. But we're not going to design new robots here, right? That's a really cool space. Lots of folks in the mechanical engineering department do great work there, but that's not going to be the focus here. Okay, so the concrete things that we are going to do, right? We have a couple of modules. The first is localization, estimating the state. Your car is navigating around an arena. You don't know where you are. You have sensors, but they're noisy. How do you integrate those sensor readings to tell you exactly where you are in the world? Right? The next thing we're going to think about is planning, which is saying, okay, now I know where I am. Then I know where I am in the world. I'm over here. I want to get from here to up there. How do I figure out what the series of motions are that take me from A to B? Now, this seems like a silly problem, right? Like we can all solve it. What makes it hard? Yeah. Telling your computer how to do it, for sure. But like, let's say you guys are taking an algorithms class, right? Like, I can just figure out like graph search will take me this way. Like, why won't that just solve it? Your environment isn't static. Your environment isn't static. That's a great point. Are there other things that make this hard? Yeah.
Like the actual physical capabilities of the robot.
That's right. So if you look at this figure right here, you're not like teleporting horizontally. It's a car, right? So it's non-holonomic, which means it can't just move sideways. And so you have constraints on the car. It only moves in certain directions. And so you can't like magically go this way, even if it's a collision-free path, right? You have to find a path that obeys the constraints of your system. Now, for a mobile robot, those constraints are like the dynamics of your car. How does your car behave, right? How does it deal with velocity? How does it deal with heading? How does it deal with speed? But for like a robot arm, for instance, that's trying to figure out how to navigate an arm under all the constraints of your arm. Your arm can't just teleport from one place to another, right? And you have to figure out how to navigate through this really high dimensional space to get from one place to another. Okay, so that's planning. And thirdly, we will do control, right? So let's say that you figure out where you are, you figure out where you want to go, but your robot is a noisy entity, right? Your actuators don't exactly do what you want to do. Your robot model is a little wrong. Your sensors are a little noisy. And so you need to have something that gives you feedback while doing execution. Right? It's like you look at most industrial systems like your helicopters or your planes, they don't just do dead reckoning, which means they don't just like choose a path and go straight. They constantly do feedback. And so they're looking at where they are versus where they want to be and adjusting their path all the time. And so we're going to cover a bunch of feedback control techniques that are going to tell your robot how to follow a plan. Right? And so we want to figure out where we are. We want to figure out a plan to get to where we want to be. And then we want to figure out how to like actuate the low level to follow that plan under the constraints that the robot is noisy and it's wrong and the model is wrong and the world can keep changing, right? And so that's what control is all about. Okay, so those are 3 of the modules we're going to cover in more detail. Any questions? And then we'll cover a little bit of mapping, but not a lot. But basically the same techniques we're going to use for localization, figure out where you are, you can also use for mapping. So you can use a similar set of techniques that you use to figure out your state of the world from noisy sensors to figure out the state of the world and the environment from noisy sensors. We're going to cast it as a similar problem. We're also going to think a lot about machine learning. So we're going to have 4 modules in this class: localization, planning, control, and learning, right? And learning, we're going to try and figure out if we had data in the world, how do we use that data to make decisions? And we're going to show that it's not just the same as any other machine learning problem. It's not just NLP or computer vision. There's unique parts to making sequential decisions in the world that make this different, right? And lastly, we're going to teach you guys how to become great robot programmers, right? And so we're going to teach you the fundamentals of ROS, which is robot operating system, right? And we're going to teach you, the elements of a robotic system, which things you need to debug, which things you need to be careful of, which parameters you need to tune. And so we're going to teach you the process of becoming great robot software engineers. Okay. And hopefully, we can use a lot of these techniques to develop things like this. So this is a video from Skydio. Skydio is or was a drone company. And they were largely for photography, but you can see that this is a hard problem because people are changing all the time. You can see the robot is trying to localize itself, it's trying to localize the person, the environment is unknown. You're on some forest trails, right? And so, and you're moving at high velocity, so you can't just go left and right, like a drone has dynamics too, right? And so, a lot of the same techniques we're going to cover in this class should give you robots like this, good engineering. And so drone technology has only gotten better since this video has been taken, but it's pretty cool. Here's another one directly from UW, actually. This is a program called DARPA Racer. They're trying to do autonomous navigation in off-road environments. So they're trying to do high-speed navigation in the mud and the grass and rocky terrain. So there's a ranch in Ellensburg, hour or two from here, and this is some of the runs of autonomous navigation in the ranch. So you can see that it's going down pretty steep hills and navigating pretty treacherous terrain, all autonomous. And so a lot of it's actually built pretty directly on top of the techniques we're going to cover in this class. So it's built directly on localization, planning, control, and learning. And so hopefully at the end of this class, we'll have a final project that looks like that. So what makes it difficult is you have to navigate through like pretty low visibility. I don't think you can really trust your sensors in the face of mud and rain and brush and these kinds of things. And so you have to figure out how to be really, really robust in the face of those things. Cool. And this is the one I'm most partial to. This is an example from this company called Physical Intelligence. And they do machine learning for robotics, right? So they develop these foundation models for robotics. And the premise is you're going to collect a lot of data. You're going to train these So this is a vision language model like ChatGPT or Claude or whatever. Basically running a robot to make coffee for 13 hours straight. I wouldn't say it's at the level of one of those vision language models yet, but it's very, very capable. And it's able to do things with high precision, high dexterity, deal with unexpected scenarios. And the cool thing about this particular example is that it keeps getting better. And so it uses ideas from reinforcement learning to say that if I keep collecting more data, autonomously, I should keep getting better over time. Right? And so in some sense, it's a continual learning system. Like the longer you spend in the environment with this robot, the better it should get. Right? And so you'll see that like over 13 hours of deployment, the robot gets more and more and more adaptive. Start, you'll have some intervention, and it gets less and less and less. And then you're able to build things like boxes or make coffee, do laundry. And you're able to do this in new environments pretty easily. It's not all rosy, it doesn't work perfectly, but I think it's pretty awesome. Doing this allows you to see some mistakes and learn quickly. And we found that for this laundry task, these models that are trained with their own experience tend to be more decisive and have more success. This is sped up 20x though, if you look at it in the bottom. So if you look at it in person, it's much slower and much less. I've also sped it up 2x on top of the 20x. So it's actually 40x. But it's able to do some pretty cool stuff. Okay. So objective 1, we're going to program race cars. Objective 2 is we're going to teach you a fundamental set of tools that'll help you build demos like that and build robot systems like that. And objective 3 is we hope that you'll all become researchers and do research with us. And so we're going to teach you how to read and understand and analyze research papers and propose your own research ideas. Right? And so the elements of this class is not just like we're going to teach you stuff from 50 years ago. We're going to teach you stuff, and then we're going to propose brand new ideas and have you defend and elaborate on those ideas yourselves. Right? Okay. So that's what you should expect from CSE 478. And if we don't fulfill any of that, hold me to it. Any questions, thoughts, feelings, concerns? No? Okay. So let's get into some logistics, right? This is oh, that's a weird one. Sorry, that's my animation mistake, I think. But this is going to be 3 times a week. So we're going to have Monday, Wednesday, Friday lectures from 8:30 to 9:20. I'm going to teach 2 modules, and Sid is going to teach 2 modules, right? And so we're gonna be co-instructors as a new experiment. And we have 3 TAs who are all sitting on that bench over there. And so hopefully they can help you with all the low-level hardware things that is going to take up most of your quarter, right? So Sid and I don't know that much. The TAs are really the people you wanna befriend. Okay. Um, who am I? My name is Abhishek. As I said earlier, I started here in 2022, so I don't think I'm new anymore, but newish. Um, I was born in Oregon and I went to India to get some culture. Got back here in 2011. I was in Berkeley for 10 years, did my undergrad and grad school there. And then I went to MIT for a quick postdoc, and then I was here. And so, go Bears. Um, I generally try to think about problems in reinforcement learning applied to robotics. So a lot of my research is how do we get robots to keep learning as they take more and more time in an environment, right? So we want to build continually learning systems that get better 1 week after deployment, much better than they are on day one, right? And so I want to have a robot that you deploy in your house, you deploy in your grocery store, in your hospital, and it's better 1 week later, right? And so the plain old techniques of supervised learning are not going to scale. And so that's kind of a lot of what we think about research-wise. In the time that I get outside of work, I enjoy sports. So I do tennis and soccer. I like to run. I've been convincing my wife to get a dog, so hopefully we'll get a dog soon. But that's kind of what I enjoy. Um, is Sid here? No, right? Okay, I will introduce Sid. Sid is a legend in robotics. He's a professor in CSE. He's actually invented a lot of the techniques that we're talking about in this class. So it's really a privilege to have him lecture with me. He thinks a lot about motion planning, human-robot interaction, adaptive control. And so a lot of what he's thinking about is how do we get robots to be really fast, really capable in really, really high reliability ways, right? So you want to deploy them in a factory. Like he was at Amazon for a long time leading the robotics efforts. And we want to think about how do we deploy robots reliably in the like millions of robot scale. And so he's also a great tennis player, loves cooking, can attest. Um, and if you want to bribe him, cheese Danish apparently is the way. All right, I'll let the TAs introduce themselves. Go ahead, Carolyn.
Robots with extra scans that give you approach. So they can react, for example, to different force profile, display, recognizing the materials and stuff like that. I've been also focusing on like self-supervised methods. So from those sensors, we can interpret those signals in a way that is compatible later to the tasks and the unique representation. And outside the work, oh, that's funny. I haven't thought of that for 5 years. I really enjoy oil painting, puzzles, I love puzzles, reading, discovering cities. I was in Boston during last fall, and I really enjoyed those walking around the city, talking to people, going to coffee shops and stuff like that. With Anton, we created this class last winter, so hopefully that will feel in winter. Yeah, happy to welcome you this topic.
Anton, go ahead.
Please, the bottom line of my salvation. My research interests focus on the application of remote learning and teaching learning on a natural populations. And it's my second time to attend South Carolina, and nice to meet you.
Rishabh?
Sure, hi, I'm Rishab. It's my first time taking this course, so please go easy on me. I enjoy path learning. I've been doing it with Professor Joshua Smith for the last year. And I guess outside of class, I like basketball and video games. Like pretty much a lot of these. So feel free to ask questions and hopefully you have a good time with this class.
Rishabh took this class last year with us and did great, so bother him with all your questions. He's the most up to date. Alrighty. I generally like to do intros to understand who everyone is. I figured we could go around and introduce ourselves. Sorry. All right, so maybe we go around, introduce ourselves, just say who you are, what year you are, and maybe let's do what is one awesome thing you want a robot to do in the next year, or your favorite experience with robots so far? Right? Low pressure. You don't have to say something interesting about yourself. It's easier. So just one exciting thing you want a robot to do, or been your favorite robotics experience so far, right? Do you want to start? Yeah.
My name is Isaac. I'm a third year here. That's one interesting thing. Well, I learned how to fly FPV drones this summer, and so I think it would be cool to program them to move on their own because they're also hard to fly. So if I didn't have to, I don't know.
Awesome. Thanks. Good.
I'm Aaron. I'm a second year at CS, and it'd be cool if you could have like a drone that does missions.
Oh, well, okay. Okay. That's awesome.
My name is Sir. So third year, and so maybe I can apply some of these and make my old car off.
Oh, nice. Okay. Don't put it on the road just yet. Yeah, good.
My name is Jay. I'm a senior, and I really like Waymo, and that's why I think it would be cool to do more self-driving cars.
Awesome. Have you ridden in
Yeah,
the
driverless
Waymos?
Waymo. Yeah, it's really.
There's some in Seattle now, I saw. I
Yeah.
saw one outside Gates the other day, so it's stressful. Good.
My name is Margaret, the second year, and there was something with full robot could do, maybe make my bed in the morning.
Nice. Okay. Well, the people at Pi actually had bed making as their last exercise, so watch out. But
My name's Forrest. I'm a senior. I would love to see Waymo offer rides in Seattle.
good.
Hi, my name is Ethan. I'm a fourth year. Perhaps I didn't see a robot. Was my laundry a little bit faster than.
Yeah,
Yeah.
that's good. Good.
I'm Brent. I'm a fourth year. And I was in my friend's Tesla and he has a self-driving feature. And we're how stressed it is. So it was fun.
It's good, right? Yeah, we got a Tesla and my wife refused to like use it because she's seen my robots failing so much. He never let us turn it on. But go ahead. Yeah.
And I also the full self-driving.
Hi, my name is Spencer. I'm a third year in CS, and I think what Boston Dynamics is doing is really cool movement and being back.
You should, we have a spot in the laptop here. You should come check it out. It's good. It's very good. It's very good.
My name is Ivan. I'm a second year, and I drove up to Vancouver for the summer in Tesla. And I was a bit tired, so I was using a lot of time, a bit too much.
Oh, really?
I think I had a bad experience there.
Oh, no. It is like,
It didn't crash, but like
I did.
I don't trust robots as much as I should now.
This summer?
This summer.
Oof. That's rough. Okay. Good enough.
Oh, so I'm an Indian student. And I invest in my stuff.
So you should tell us what should we see in our next phase of robotic strategy?
Yeah, absolutely. I'm Will. I'm a third year in CS, and the thing I'd like to see a robot do would be just more expanded self-driving and like more brands than just Tesla. But have them be more consistent.
What do you think is stopping it from expanding with the data gap? Is the tech gap?
It's tech, I think it's like because the only car I believe that has like full like GPU setup or like the main one, I believe, is like Tesla, so you can't really do full self-driving currently on most of it. Yeah, so.
Hi, my name's Amrit. I'm a third year in CS, and I like this a little bit.
Nice. Good.
I'm doing a third year in CE, and I would like to explore, I think helping on like sort of give that out. I don't feel like I like.
Yeah, yeah. That's-
I'm Ruby. I was like here in engineering. I think I would like to see a robot who like runs my errands for me or picks up stuff.
The word robot actually came from drudgery and forced labor, and so it's meant to do that. So maybe back there. Yeah. Nice.
I'm Desmond. I'm also from MSTI and I want to have a robot play games.
Nice. I can do that right now, I think. Chess and stuff. But I wouldn't trust him. Go ahead. Okay, awesome. Great class for you. You wanna go back to? I'll use this.
I'm Lynn, I'm a fifth year master at CS. Yeah, same experience, and I'm very impressed when I was on my friend's Tesla 2 days ago. The total self-driving, it's laid out. That's crazy.
Yeah.
So, I think compared to Waymo, which has way more sensitive, I don't know how like Tesla actually achieved that is actually doing a good job, so.
Yeah, I agree. In Seattle, it feels a little scary with all the rain because your cameras are blocked all the time, but it works. It works somehow. I'm good.
There's my. CS, there, and I think grow with that. Awesome. But my name's Vernon. I'm in the third year, and I think seeing robots interact with physical hardware systems. Like machine vending. Yeah, kind of like. They probably have the software to hack into systems, but now they can also physically get. Oh yeah.
I see. Nefarious purposes.
My name is Kevin. I'm a fourth year. I'd love to see Vivian succeed in doing personal level 4 something.
Nice. Why living?
Hey, or even good things.
Yeah.
Yeah, my name is Namkesh. I'm a third year. And just interested in like getting into the large research, and so this is awesome.
Awesome. What kind of research do you want to do? Awesome. Cool. Right.
I'm third year CS student. I like a robot to play like competitive sports, maybe like table tennis or something. That would be cool.
Nice. There's some cool stuff coming out of Amazon where they're like getting the robots to play table tennis and stuff. You should check it out. Yeah, it's cool.
I should come third year. I want to see a robot play.
Ah, wow. Well, Entong's working on dexterity. You should work with Entong. Go ahead. Yeah. Ah, nice. That's hard. Yeah. Good. Oh, nice. Yeah, that's very cool. Good. Me too. That would be great. Thanks. Well, hopefully we can achieve all those dreams by the end of the winter quarter. And so let's keep going. But yeah, thanks all. Okay. So the thing you all care about, grading, right? How does grading work in this course? Generally, I'm a super easy grader. You guys gonna get great grades in my class. I don't care that much. But the way that we break the grading up is we have 4 different parts. The first is your programming projects, which is the biggest part of the class, right? So they're projects that are jointly done in simulation and in the real world, right? And so you'll have 4 projects, each of them graded at 10%. And they're just pass or no pass. There's no like grading. You just have to get it to work. And the TAs will help you a bunch. I'll help you a bunch. Sid will help you a bunch. So it shouldn't be super hard, but it does take a lot of time, right? And so that's going to take up a lot of your time. The next two things are seeded paper discussions, which are a new thing that we're trying. And so seeded paper discussions are trying to get you to be researchers. And so the way we're going to do it is we're going to send you to, this is a group-based class. So everyone's divided into groups, right? And so each group gets 2 seed papers. And so each of these seed papers are going to present like some ideas. And based on those ideas, we want you to propose follow-up papers and follow-up ideas, right? And so we want you to propose a new research idea, propose why it makes sense, defend it, right? I'll send you some examples from last year, but it was a lot of fun. The next is we'll do quizzes. So there'll be 4 quizzes. And then we'll drop the lowest one, right? They're 15 minutes in class, pen and paper, so we can't chat GPT the whole thing. And we're just going to test like knowledge from each module, right? So there's 4 modules, 4 quizzes. Shouldn't be too hard. We're not going to try and trick you. And lastly, there's the final project. The final project is trying to put together the first 4 projects. Right? So you're going to have a intro project, localization, planning, and control project. You put them together to get a car that navigates fully autonomously. Right? And so that's the final project. That's 10% of your grade. It's due on the last day of the quarter. Right? And then we'll have extra credit. I'll just make up some homework on probably imitation learning or reinforcement learning. And so if you want to have fun with that, you can do the extra credit. Okay, so that's the general structure. Let's get into the details a little bit, right? So we're going to have these 4 projects. Right? So we're going to have the intro project, which is just trying to get you familiar with ROS and these kinds of robot programming languages. We're then going to have the first project, which is on, or like the first project, which is on localization, and have the robot figure out where it is, right? And so that's going to be based on the first module of the class. The next project is going to be on control, which is saying that you want to follow a path accurately despite noise. The next project is going to be on planning, which is trying to plan global paths to navigate around obstacles and get through hallways and so on. Right? And so we're going to have teams of 4 or 5 across all of these projects, and we'll have them all be auto-graded, right? And so you should know exactly how well you're doing, right? But as you'll find out, things on hardware are not the same as things in software. And so getting things to work on the robot is a huge pain in the ass. And so you need to devote enough time to it. Okay. The way that these seeded paper discussions will work, we tried it for the first time last year. But basically, we want you to take these seed ideas and propose a new paper level idea, something that you would implement in a research project. Right? And so it's like, let's say we gave you a paper about like model predictive control. We want you to find what is wrong with that, right? And what new ideas you have from them. We want you to tell us what the motivation is. What is your key technical idea? How would you validate it? We don't need you to validate it. If you want to validate it, that's great. But really, we just want you to tell us what your experimental plan is going to be and then place it in the context of the literature. Right? So we want you to say that this is how it would affect the literature, which things would push forward. And it's kind of going through the exercise that we all go through when we're doing research projects. And just so that everyone is involved, those who are not, each person will get a chance to present. But the weeks that you're not presenting, we want you to propose constructive feedback and commentary. Don't be an asshole. Just like to help your teammates or your classmates do better. Right? Okay, quizzes, pretty standard. Just going to be MCQ. There'll be some problem-solving questions, some conceptual knowledge questions. It's going to be 15 minutes. No laptops or phones. Don't cheat. It'll be easy enough. Okay, and the final project is really a combination of all the previous 4. And so this example here is from one of the final projects a couple of years ago. And one of the cool things in this class is depending on how much effort you put into your algorithms, you can get your cars to do more reliable and faster things. And so we're going to have a special prize for the top 3 teams in terms of how fast they go around the track. So if you want to do more, we'll give you a little trophy. Okay, the next thing is please come to class and participate. I hate monologuing, it's super boring. I'd love to interact with you all and have you all participate. You could just chat GPT the whole class. So the whole point of this class is to come and interact with me and Sid and the TAs and kind of learn things and and go beyond just like what you can Google, right? And so you kind of don't get what you're looking for out of the class unless you participate, right? Okay, so the structure of the class is going to be the first week is just going to be an intro, trying to lay out like what formalisms we're going to use, what mathematical structures we're going to use, and kind of getting it situated. We'll then cover state estimation, and I'm going to do that. The next two modules are going to be control and planning. And then the last module is going to be learning, right? And so we're going to have me do modules on state estimation and learning, and Sid do the modules in between. And then we get to March and we should be done. Okay. Any questions so far? Yes. Sorry.
What's quiz section for?
What's the quiz section for?
Yeah, just in general, do we take quizzes in quiz section or it's just general?
Oh, you mean when you register? Like what? Yeah, I would say just like the way that it's going to work is that you'll have lecture and then you'll have labs. So you have access to the lab where you can go do work on the car. And then you'll have labs which are guided by TAs. But there's no like, I think the quiz section thing is just like a holdover of the system. So don't like there'll be in-class quizzes, and we posted them on the website when the quizzes are. There'll be 4 quizzes. But there's no quiz section. Yeah, so really what you need to focus on is the lecture, and then like the labs, there's 4, I think I have it in. Sorry. Like there are these 4 lab office hours, right? And you like those are times where you get help from the TAs, and other times you can come in unguided. But like don't worry about the quiz hours, and you don't need it. Yeah.
Just ignore that time.
Ignore that absolutely.
Police pop quiz or
No, we're gonna tell you. No, I'm not gonna tell you. Yeah, we'll tell you when they are beforehand. It's just gonna be 15 minutes, like a couple of questions on MCQ.
The self-guided or
We typically, so the way we do it is we send out a knowledge quiz, which we'll send out today or tomorrow, and just to gauge everyone's familiarity, and then we try to make teams with like roughly balanced knowledge ourselves. If you feel strongly about being paired with someone, let us know. There's a section in that form to let us know if you want to be paired with someone, and we'll take that. Any more questions? Okay, so as I was just saying, as I was just saying to Isaac, we will assign teams. I think we're 42 in the class, so we'll probably have 10 teams or 8 teams of 9, 8 teams of 10, and 2 teams of 5. I think that's right. Yeah. Where we will post this knowledge survey on the website, and on all my communication will be through EdSTEM. And that would be the easiest. You just need to fill that out with what you're familiar with, and we'll make the teams and indicate to us if you really want to be paired with someone. But the hope is that we can all mingle and learn from each other, right? And typically we'll have the same teams, but if there are any issues, please let me know immediately, right? And I'll address them. Like in the past, we've had some issues with teammates not getting along and these kinds of things. We don't want that. We want you to have a good time at the class, so please let us know ASAP and we'll change it. It's not a problem. Okay. And if you feel like this team isn't working and you're not just yelling or your schedules don't work, let us know early, and like in the first few weeks, we can swap things out. Okay. One thing we've had an issue with in previous classes is, you know how group projects are. There's like 2 people who do all the work and then 3 people who just sit around. And that's really frustrating for everyone, right? And so what we're going to do is we're going to have an anonymous survey at the end of every project where you rank your peer or you evaluate your peers. And so you say that if you felt like some of your peers just didn't do anything, we'll give you an opportunity to say that. Right? It'll be anonymous and you don't have to, it just factored into your grades behind the scenes, but I'm not fixed on this. This is just the best I could think of. But what's really frustrating for lots of people in this class is the group project and 2 people do all the work and everyone else just guess its own. So if you guys have ideas on better things to do, let me know, but this is what I could think of. Any thoughts? Are there things that have worked in other classes? Or are we okay just like not doing this and just letting the forces that will govern group projects? How do you guys think about it? I'm not going to be frustrated. You're going to be frustrated. So you tell me. You're good with it? You good with this? Any objections? You don't feel like comfortable saying it right now, please come talk to me after class and we can address it. Okay. So we don't want one person putting the whole team on their back. Okay, so we're gonna have all 4 assignments are gonna have 2 parts. Actually the first one has no hardware, but the next 3 assignments will have 2 parts, a simulation part where you test your algorithm in simulation, make sure it passes the test, and then one on the real robot. The real robot takes 90% of the time. The simulation is often easy, right? And so it often takes a long time to tune the robot, to deal with hardware issues. Like that's part of the process. And so make sure you devote enough time for every project. The way we're gonna do office hours is that I will do conceptual office hours. I'm not going to be that helpful to you on the labs. The TAs are much more helpful to you on the labs. I can help you somewhat, but we're going to have to figure it out together. Whereas the TAs have tested and done all the homeworks themselves, and they should be really helpful. And so we have 4 different office hours on basically every day of the week except for Monday, where you can go in. The TAs will be there. They can help you with your projects, right? Don't ask them to do it for you, but besides that. And any other time you want to reach me or the staff, just email us and we're happy to meet. And anytime you want to use the resources, come in and use them unguided. But like don't make a mess in the lab. That's it. The room for the labs is in Allen 002. It's in the basement of Allen. And so you all should have keycard access to, if you're registered in the class, you should have keycard access to Allen. But if not, just let us know and we'll activate that. Okay, so the Allen lab is basically just a space. So if you go in there, there's a bunch of desktops. Each team will be assigned a desktop and a car, right? And you already have a bunch of the libraries installed for you, like a lot of it is done for you. But there's like a region where you have to practice your navigation stuff. And there's a region where you can work on the cars and the hardware, right? So each team gets 1 race car. If the race cars often break, as hardware does, in that case, the TAs will help you fix it, but don't go crazy. We only have a finite number of race cars. So, but we will help you replace cars that get damaged. Right? So generally, don't crash your cars into the walls all the time. Like try to be careful with them. Don't change the password on the cars. Like a bunch of stuff is the IP and stuff is registered through that. So don't mess with it. Generally, the batteries are these lithium-ion batteries, and so you want to be safe. There's like a battery bag that comes with each of them, so make sure to put it in there. And don't take the cars home. Like they have to stay in Allen, right? So you can come in anytime you want, but just don't take them home. I have to track you down. It's a mess. And so if you can just keep them there, that makes life easier. Right? Any questions? So once we have the teams assigned, we will send you guys, there'll be 2 special office hours where you can pick up your cars and you can get assigned your desktops and you can get started. Okay? And so the first homework doesn't actually need the car. And so, but from the second homework onwards, you want to use the car. Okay. Yeah, this just don't cheat. Right. I think there's not a lot of merit to ChatGPT all the homework. Like you could do that, but you don't learn anything, right? So I would say also you can't ChatGPT parameter tuning on hardware. So I would say if you can, try to do the homework yourself. You can discuss things with your teammates, just acknowledge it in your report, right? Or discuss things with other teams, just acknowledge it in your report, and every team should write their own report. Okay, I think we are at 9:20. Any other questions before we end for today? Yeah. So there's a VM that allows you to do it on your own computer, so you don't have to deal with the pain of installing it and stuff. But you can either use the workstations or do it on your own computer through the VM. Awesome. All right. Yeah.
This section is still on.
Just ignore the section. Only focus on the office hours and the lab. They're on the website and they're on my slide.
Oh, does the course website?
The course website. All right. Thank you.